Hi there, my name is Dickson. I am an award-winning and multilingual tutor here at the Profs, and I specialize in subject tutoring in maths, economics, Mandarin for GCSE and A levels, as well as 11 plus 13 plus 16 plus entrance exam in Cat 4 and ISEB for UK's most competitive independent and grammar school admissions. Students that I currently tutored or have tutored are studying in top UK schools like King's School Wimbledon, Cheltenham Ladies, Wickham Abbey, etc. And also some of the best UK universities like LSE, Cambridge, Oxford, UCL, King's College London, etc. 97% of my A-level students achieve a success rate of getting at least a grade B or higher, and 72% of them getting A stars and A's. And I also boast a 100% success rate for my GCSE students achieving at least a grade 6. Today, I want to discuss with you one of the hardest A-levels past exam questions. So this is taken from the EdXL 2022 maths paper. This was branded as one of the most difficult questions for students because this question is out of 9 marks. The average score of this mark is less than 2 out of 9, making it truly one of the most difficult questions in past papers. So today I'm going to show you how to solve this and also break down the steps and to show you how to break down a complex question into simpler steps, as well as breaking down the multi-steps into a logical sequence. So we have here as an example. As you can see, we've got a curve here. The question is broken into 2 parts. The first part, they want you to show that the area underneath the curve can be shown like this. And part B, after you've done that, they want you to find the exact area of R, which is this part here. So let's begin with part A. Because they want us to show the area underneath the curve, the first thing we should do is list the equation underneath the curve. So, of course, this is the area underneath the curve where you integrate between the 2 limits in terms of x and y is the curve equation. So just by writing the equation out, straight away you're showing the examiner that you know which equation to use and you know what you're talking about. After that, we can plug in the equation from the previous page, and we were seeing that in terms of the x limit, the r was between 4 and 0. So let's write x equals to 4. And x equals to 0 here for the limits. And then let's plug in the equation for y. As we recall, that the y is equal to 2 sine 2t plus 3 sine t. And then dx. Now, we have a problem here because, as you can see, we are integrating with respect to x. Yet our equation is in terms of t. That presents a problem. So what we need to do is turn the limits and the dx into t. So the limits are quite straightforward. All you have to do is plug in the upper limit and the lower limit into the x equation. For time purposes, I've done it already. That will give us pi over 4 and 0. This equation is here to stay. So we rewrite that 2 sine 2t plus 3 sine t. Now, the problem is the dx, because we are integrating with respect to t now, not in terms of x. So what we can do is multiply the dx by dt, but also at the same time divided by dt. We can do this because dt divided by dt is just 1. And of course, you're allowed to times anything by 1 or divide anything by 1 without altering the answer. So this is a good start. The next thing we have to do, of course, is to put in this dx dt, which means differentiate the x equation. Recall what the x equation was. The x equation was x is equals to 8 sine squared t. So when we differentiate this, we will do dx dt. As with differentiation, you bring the power down. So that becomes 2, and then you got sine t. Now, this sine t originally was a square, so after you differentiate, the power goes down to 1. So we don't have to write it, we can just write sine t. But then we're also going to differentiate what's inside the bracket. So this means that we have to differentiate times by the differential of sine t, which is cos t. These two combine to give us 16 sine t cos t. So once we found this, now we can put it back into this equation. As we can see, we will have 2 sine 2t plus 3 sine t times the dx dt that I just found, which is 16 sine t cos q. Now, as you can see that I also have to have the dt here. So I add it right here. And we've done the part where we need to change all the x's to t. As you can see, there's no more x in this new equation here. The next thing we can do is simplify this by multiplying the 16 sine t cos t into this bracket here. That gives us 32 sine 2t sine t cos t plus 48 sine squared t cos t dt. So this is where we got up to now. As you can see, here we have 3 different terms together, sine 2t, sine t, and cos t. That's going to be difficult later on when we integrate. So what we need to do is simplify this section here. So what we're going to do is think about what we know with regards to sine 2t that can merge with sine t cos t. Well, what are the identities springs to mind? We know that sine 2t is equals to 2 sine t cos t. And that's great. Because of this, we can immediately replace what we have with sine 2 sine t cos t into sine 2t. So let me go ahead and rewrite that. If I times 2 sine t cos t and I replace this section here, this is going to give me 64 sine squared t cos squared t. And the second part remains unchanged, so 48 sine squared t cos t dt. Okay. Now, if we compare what we've accomplished so far versus what we ultimately want, this is an exam technique. When you work through the question after every couple of steps, check back ultimately what is it that you're trying to achieve. In this case, the question says, show that the area underneath the curve can be equals to this. They want us to show this. This is the last line of our part A. So look at where we are right now. So where we need to finish. As you can see, we've already done half of it. This part here is exactly what we've done here. So that means the remaining part is we got to find a way to turn this into this. And what's the biggest difference? What's stopping us right now is this part here. We have the cos 4t, but so far what we have is sine squared t, cos squared t. So the thing we should do now is to think of a trigonometric identity that we know that connects cos 4t and sine squared t cos t. Well, one of them springs to mind. Is the identity cos 2t. This is going to equals to 2 cos squared t minus 1. Now, I can manipulate this because if you saw just now, we want cos 4t, not cos 2t. So that means I can just double the angles here. So instead, I'm going to have cos 4t equals to 2 cos square 2t minus 1. So now we got this. We are up to 2 cos square 2t minus 1. Now, one of the very first identity that you've learned can actually help us here. It may not be immediately recognizable because we got a 2t here. But imagine the 2t is x or another letter. That will be the very first identity you learn, which is cos squared t plus sine squared t equals to 1. Now, we have cos squared 2t though. Does it make a difference? Not really, because all we have to do is change both of these letters from t to 2t. So let's do that. Great. And now I'm going to move the sine squared 2t to the other side so I can isolate what I want, which is cos squared 2t. And now I can simply replace this into here because this is cos squared 2t and this is cos squared 2t. So I'm going to sub it into here. I'm going to end up getting 2, 1 minus sine squared t, close bracket, minus 1. I then proceed to multiply out the bracket. This is going to be 2 times 1, 2 times 1, and then take away 1. That's just 1. And then 2 times minus sine squared t, that's minus 2 sine squared t. Okay. Now, with sine squared t, we know that we have, sorry, this should be 2t here. With sine squared 2t, this is basically sine 2t times sine 2t. But look at what we've done up here. Sine 2t is 2 sine t cos t, and we're squaring this. So that tells us we're doing this thing times itself again. So we are, instead of writing sine 2t times sine 2t, we're going to say 2 sine t cos t times 2 sine t cos t. And that's your square. So let's square it. That gives us 4 sine squared t cos squared t. If I then multiply the 2 into here, that is 1 minus 8 sine squared t cos squared t. Now, as I said just now, every time you've done a couple of steps, you got to take a little pause and then check what you're doing. Look at this and look at this. Now we're getting very close. We have the sine squared t cos squared t. We also have the sine squared t cos squared t. The only difference is the coefficient in front. This is the 64 and this is the 8. So how can I turn from 8 to 64? Just times everything by 8. Recall what we've been doing here so far. We started off with cos 4t, which is here. We built the cos 4t from here, and then we carry on building our logical sequence here. So this is in fact cos 4t. Now, what I'm going to do, as I said just now, I'm going to times everything by 8. Times this by 8, times this by 8, times this by 8. So that's going to give me 8 cos 4t equals to 8 minus 64 sine squared t cos squared t. I'm going to bring the minus 64 sine squared t cos t to this side. And at the same time, I'm going to bring 8 cos 4t to the other side. So I'm just going to swap these two. So this is going to become 64 sine squared t cos squared t equals to 8 minus 8 cos 4t. Okay, I've managed to make this equals to this now. So the last step, of course, is just to replace this into here. So that's going to give me pi over 4 and 0 as the limits unchanged. Now I'm going to replace, which is 8 minus 8 cos 4t plus the remaining part that I haven't touched. And guess what? Now we check what we've done so far. So what the question was asking us to prove, 8 minus 8 cos 4t equals 48 sine squared t cos t. 8 minus 8 cos t plus 48 sine squared t cos t. And we're done. So now we're done with part A. And the good thing is we know for sure we got it right because whatever we've shown here is exactly what the question is asking us to show. So now most of the hard work is done. Now we got to find out what is the exact area of R using this equation. So let's go on to a new page and I'll show you how it's done. So on the first piece of paper, I've just brought the same equation over just so we got no space. So now we move on to part B to find the area of R between the limits t equals to pi over 4 and t equals to 0. We've already done the hard work. Now it's all about integration. Now, a common mistake people made would have tried to integrate the original equation, but that would have made your work in part A render completely pointless. The reason why they get you to do part A is to say, hey, you have shown the area underneath the curve can be expressed this way. So now hence, look for the word hence. Hence means use what you've done in the previous part to help you in the subsequent part of the question. So hence, we are going to use what we've done in part A to integrate, not the original equation. Otherwise, we won't need to do part A. So let's integrate this. When we integrate 8, that's going to give us 80. If we integrate 8 cos 40, what do we get? Well, the 8 stays there. We know that when we integrate cos, that's going to give us sine. And when we integrate, we also have to divide by the differential of this. If we were to divide by the differential of 40, that's going to be divided by 4. So remember, we could do both of them. As I said, the cos 40 becomes sine 40. But we've also then got to divide by the differential of 40, which is 4. So we got to divide it by 4. Oh. Okay, and this is the part where a lot of students would have struggled, because you got 3 different terms here. What do you do? Now, if you notice here that when you differentiate sine t, you get cos t. So on side, what you can always try when you got 2 terms combined where one of them is the differential of the other one, you can try the original function plus the power of 1. So here, I'm going to test it by saying sine t to the power of 3. Because when I differentiate sine, I get cos. So I add the power by 1. I'm going to test this. If I differentiate this, this is going to bring down the power. So 3 sine t. Subtract the power by 1, which is 2. And then differentiate what's in the bracket, which is sine t, which is cos t. So if I differentiate this, I get this. Now, compare what we got here, the differentiated version, with what we have up here. What's the difference? It's just a number. So that means I can change this to 48 because I multiplied this by 16 if I also add a 16 here. Because when you times this by 16, you can also times the constant by 16, and 3 times 16 is 48, and 48 is exactly what we will have. That means if we reverse our thinking, if we go back this way, when we integrate 48 sine squared t cos t, we're going to get 16 sine cubed t. So that is what we're going to do. All right. And don't forget to put the big brackets here, which tells the examiner that you've done the integration now. And we put the limits here. Okay, the hardest part is done. Now it's about subbing in the limits. So the way integration works is that you put in t equals to pi over 4 in here, wherever you see t, and then subtract the same, but when you put 0 into here. So if I replace the pi over 4, I get 8 times pi over 4 minus 8 divided by 4 is just 2. So 2 sine 4 times pi over 4 plus 16 sine pi over 4 to the power of 3. All of this will go on then subtract. Now we do the same, but this time with 0. So 8 times 0 minus 2 sine 4 times 0 plus 16 sine 0 cubed. And now all you have to do is put all of this into your calculator. Now, obviously, you can see all of this down here. All of this is going to give you 0. 8 times 0 is 0. Sine 0 is 0. Sine 0 is 0. So we know all of this is going to be 0. Here, 8 times pi over 4, that's just going to be 2 pi. And then you have 2 sine 4 times pi over 4, which is just sine pi. Sine pi is just going to be 0 again. And here, you got 16 times sine of pi over 4 cubed. If you do that, just put this in your calculator as an exact number. That will give you 4√2. The question asks us to express it in an exact value. This is exact. Another common mistake that students make will be to do all of this in the calculator, write this very long equation in the calculator, and the calculator end up giving them a decimal. A decimal is not exact, especially when it's recurring. So to leave it as an exact way, this is the way to do it. And also, don't put long equations into the calculator, because all you have to do is make one little mistake and your whole answer will be wrong. Break it down. If you choose to do it, put this section in the calculator first, and then put this section in the calculator, instead of doing it in whole go. So there we have it. That would be what you get if you put in your calculator, and that's the exact answer for part B. And with that, that's 9 out of 9. If you found this video to be useful, please give it a like and subscribe to our channel, where we give tutees like you the insider knowledge you need to solve difficult questions like these and to also boost your grade. Together, we will help you get ahead at school and help you achieve the best grades possible and maximize your academic potential. If you're interested in learning more about A-level maths or maths in general, please don't hesitate to contact me and our team of professionals. The contact information is on your screen right now. I'm Dickson from the Profs. Thank you for watching, and I wish you the very best of luck with your studies.